So what we did in the last class was, I think, potential energy relation and conservative force dependence on potential and vice versa. So we saw two things basically, which the first one was a del operator, which is a short notation for partial derivative of in three different directions, three mutually perpendicular direction, and then putting the ijk like this. So we saw this del operator in the last lecture, right? And then what I said that the force as a vector is a negative of del of u. So the name which I gave to this some term symbol was a gradient, and a gradient is a generalization to the word slope. Okay, more general form of slope. Now, slope is something which we use for one dimension, in which we have a single dependence of things. So when we say that y equals to f of x, then dy by dx, because it's only one variable thing, we call it slope. But if we have something called, let's say, w, which is a function of x, y, and z, then there is nothing like dw by dx is meaningless thing, because we have multiple variables. So what we do is we check the slope in each direction separately. So let's say if you want to check the slope, if I walk along x-axis and I want to see the change in w, this is called partial derivative, which tells you that if you walk along the x-axis, what is the change in the value of y. But because we have multiple variable, which means we can walk in different direction and we can expect some slope. So when you have a triplets of slope for each direction, so we can bring all three together in a single format called del, and we call it a gradient. So gradient is a collection of slope in three perpendicular directions in three dimensions. This is how you can think of. Gradient can be in any direction, to be very precise. If you have particularly, please, someone can switch off your mic because it's great. Okay. So I hope the difference between the slope and gradient is clear to all of you. So do you understand the difference? What is slope and what is gradient?
Yes.
Yes, sir.
Slope is for one dimension, like when you walk along only one direction, there is no other direction available. And the gradient is when function can change in any direction. So we define gradient, and so we define the partial derivatives like this. So now, taking a clue from the vector chapter, we know that cross product of same thing, what we get?
So
A null vector, right? So similarly, if I say dot as a some sort of vector notation, so the del cross del is also null. So now we can actually conclude from like this, and therefore we get something interesting. So any conservative force can be written as negative of potential gradient. So if I take the cross of the force, it turns out to be del cross minus del u, which is exactly what we just learned, that we can write like this, and we know that this is 0, which means When you take the cross product of the curl, this is called curl. So curl of a force will be a null vector if it is conservative. This is the mathematical test for conservative force. Okay. Now this is something difficult, very difficult for you. So how we can write in a better way, like so del cross F we can write in determinant form because it's a cross of two vectors. And if you remember the vector chapter, you can do it.
Yes.
I cap
IJK,
ijk. Then del is what?
del by del x, del by del y, del by del. And fx, fy, fz.
Correct. So if you expand, you can get something like this. I cap multiplied by del fx, del fz by del y, like this, minus del fy by del z minus j and del by del x of fz minus del by del z of fx, and last. This is the expansion. So let us check. If I give you f equals to y I cap plus x j cap, can you tell me whether it is conservative or not? It will be 2 by 2 determinant, right? So no need to put the third determinant, just write 2 by 2. I we have tried. Okay, you can make extend to 0 k cap and then just write the answer. We have tried the 3 by 3 only. Nothing is there, so you can add a 0 from your side. And then del cross f you can write as I. What is del? Okay, this is fixed. What is f? X. What is fy? And then taking the I cap, j cap, k cap. So I cap into what we can write? Del by del of 0, 0, and del by del z of x is 0. So this is 0. Because if you differentiate x with z, it is 0. And I'm sure that what you will do, you will give you 0. Because what you will get in the last is k cap into 1 minus 1, which is again 0. So this turns out to be 0. So f is so you can write like this. It is clear, guys? Hello, hello, 1, 2, 3. Any doubt in this? so far? Okay. Now we can go to the next concept that is called stability. So what is the meaning of stability is, let's say, if you keep something,
Sir, can you show the previous page? Done, done.
so we all know that the word equilibrium means that when the net force and the net torque acting on the body is zero. That's the meaning of equilibrium. So equilibrium of particle refers to when net force is zero. Equilibrium of body, when we have a shape dimension, it demands two things: that net force must be zero, as well as net torque must be zero. So when we solve the rotational dynamics question of equilibrium, we first write net force zero, and then we also write the net torque zero about some point, and then about some axis, and then we get the answer. So presently, what we are concerned is the particle. So right now we are not going deeper into the body part. That's a separate chapter called rotational dynamics. So as long as the particle is concerned, it is said to be in equilibrium if the net force is zero. So which means velocity may be constant. Equilibrium need not to be static. Equilibrium may be dynamic also. So motion may happen, but still it is in equilibrium. Understood? So this is possible.
Sir, what is that summation tau?
But then summation of tau, torque, that's torque. So don't worry, torque I have explained in the chapter of vector, but in case if you don't remember, don't worry, we'll discuss again in chapter of rotational. So first of all, the word equilibrium is important. So let's talk about the static equilibrium. So let's say a body is at rest. So the word stability will tell you that what is the probability that even if you disturb it slightly, it will be again tend to go back to the same position or may tend to go away from the position. So based on the property of the subsequent motion upon disturbance, we can decide the stability. So the simple way to understand is diagram will help you. So now we have three situations, as you can see. And if the body is at rest. So a body is at rest at the bottom of the bowl, you can see. Then so let's try to displace. No, all three balls are at rest. Now try to disturb slightly. In which case it is going to come back to the same point of equilibrium. In which case it
First,
will have tendency to go back to the equilibrium,
first case.
the first case. So if you disturb and the tendency is to go back to equilibrium position. Now the word is position. So you are disturbing and the tendency is to go back to the equilibrium position. That's the tendency. In that case, we call equilibrium as stable equilibrium. Because you want to disturb it, but it's trying to go back to the same point. In the B case, if you disturb slightly, but in the other case, if you do it, there is no question of coming back to the same point of equilibrium. So it will rather go away. Now the third is very interesting. You do whatever you want to do, it will remain there only. So there is no tendency either to go away or to go towards. It's like it's neutral. So we call it neutral equilibrium. And this we call unstable equilibrium. Okay.
Sir, can you explain the third case again?
Yeah, tell me which case.
Sir, neutral one.
In neutral, if you displace from here to here, it will neither try to go this way nor try to go this way. So there is no tendency.
Okay.
So it will remain there only, right? So in the case 2, in the B case, you can see if you displace right, it will go right. If you displace left, it will go left. In the A, if you displace right, it will go left. If you displace left, it will go right. In the third, there is no tendency to go left or right. That's why we call neutral equilibrium. So now if you try to analyze in terms of energy, the better intuition is look at the potential energy of all three cases. Let's call this as a reference. So in the case of stable equilibrium, what do you see? The potential energy is minimum or maximum or nothing. What do you see?
Sir, after it means reaches the bottom.
If this is the reference, then in which case the body is at a rest and having some potential energy. So the potential energy you have to check is the lowest, highest, or in between, or constant.
Lowest. Sir, it's lowest.
Yes. In the very first case, you can see that even if you displace right or left, it will go above in the height. So basically, when you try to displace, you raise the potential, you increase the potential. So the tendency is to go back to the non equilibrium position because the potential at equilibrium is lowest value, and the tendency is to go back to the position which offers the lowest potential energy. So that is why the ball, if you displace right or left, it will tend to go towards the position which offers least potential. Okay. So as per the design of this situation, that is called a stable equilibrium, because stable refers to the fact that we already have attained the lowest potential configuration. So below that value we cannot achieve further. So we are in the stable most condition of energy. Okay. And that's why we call it stable equilibrium. So stability has a relation with energy. So higher the energy, lower the stability. That's a simple rule of thumb in chemistry, also in physics also. So look at the case B. In case B, what do you think? The potential is maximum or minimum?
Maximum.
So if you displace towards the right or left, the tendency is to go away, because the lower energy configuration can be achieved somewhere else, not there at least. So definitely that is called the unstable equilibrium, because that stability is very poor. Like it may be at rest, but once you disturb it, the chance it will go away is 100%. So now comes the neutral equilibrium.
Constant.
The potential is constant. So no matter where you put it, the potential is not going to change. Now this idea is intuitive. The reason is because I have given you the situation wherein you can think of the gravitational potential energy. But this idea we have to translate to other form of energy, which is not gravitational, other force also, which is not gravitational, and therefore you need to develop the intuition from here. So this is a pictorial diagram to understand, but the idea will be for all situations which we cannot represent the way we did it here. Okay. So this pictorial representation is not the absolute way of thinking, but of course this is a very intuitive and informative in a way that it gives you the idea, and you can apply this. Okay. Now what we are supposed to do is we are supposed to write some condition, what could be possible in different cases. So the first case, let me write down something. So at equilibrium, the force is zero. So we'll talk about the one dimension only. And force is zero because we know force is equals to minus du by dx. Let's
Minus
say
d
one.
by dx.
So we can say the potential gradient is also zero. That's about it. Here, because everywhere we have equilibrium, so this term is zero everywhere. In the first case, the potential is minimum. So from the concept of calculus, we know that if something is at minima, the lowest potential energy, so U is minimum. So we know that if potential is minimum, it means the second derivative must be positive. That's the rule of minima. But here the potential is maximum. So second derivative must be negative. Here constant. So the second derivative is also zero. So this is the mathematical test for all three. So now this is the mathematical condition for each case. Now the first case is of great importance to us because the first case gives you something called the oscillation. So stable equilibrium is the condition in which if you disturb the body, it will oscillate. It will go left, right, left, right, left, right. So in this case, if body is displaced from its mean, also there is a name called equilibrium. These are the same thing. Position cancel. So in this case, it will perform the oscillation. And the second thing, which is very important and very point of view of examination, if the amplitude is small enough, then oscillation becomes simple harmonic motion. We call it SHM, and very soon we are going to learn after hopefully rotation chapter. So oscillation and SHM are mathematically different thing. SHM also means oscillation, but all oscillations are not SHM. So all SHMs are oscillation. Vice versa is not true. So SHM is some mathematical condition actually which we impose on the oscillation, and if you fulfill that mathematical constraint, then we call it SHM. Else we don't say. That's the idea. So only in the case of stable equilibrium it is possible. Okay. In unstable case, what happens? Particle continue moving in the direction of displacement. No restoring force. So basically here what happens? I should have written this before, but okay.
Sir, I have one more. In the second unstable equilibrium,
Yes, tell me.
sir, if we take the reference line at the where the body is kept, then the potential is minimum at that point.
Pardon?
Sir, in the second case, if we take the reference line at where the ball is kept at the topmost point, then there the potential is lowest. No?
No. If you
Then
take the reference there, then
how
if
to
you take the reference there, it will go down means negative potential. So negative is lower than zero.
okay?
Understood?
Sure.
Okay. In the neutral equilibrium, what happens? Particle so wherever you put the particle, every portion is position of equilibrium. So no matter where you keep, it will be at the equilibrium position. So that's the idea of neutral equilibrium. So I have given you the mathematical way of looking at it. So now the kind of question which you can expect is graphical as well as numerical. So if I plot a graph between potential versus x, so how many stable and how many unstable equilibrium you can see here?
So two stable and two unstable. I think.
Two stable and two unstable.
Correct. So 2 and 4 are stable and 1 and 3 are unstable.
Sir, x1 and x3 are stable and x2 and x4 are unstable.
Correct. For the obvious reason, you can draw the line and you can see it's a maxima or minima. Okay.
Sir, I want to know the last question. Done, sir. So,
Let's say we have two H item and R is the separation, maybe in the micrometer or maybe in the nanometer. So now at a larger separation, there is no interaction, so there is no potential. But as they interact, they start attracting each other, and the attraction will basically decrease the potential. till one particular value, the potential will become minimum. But if you try to go beyond this, the potential will again rise. And at a zero separation, which is not possible, it will become infinity. So it will go asymptotically very high. So now what you can realize that there is one particular point at which the potential has become minimum. So this must be the stable position of equilibrium, because we have tangent zero, and at this potential, so in this position, we call it r equals to r naught. The u is, let's call u naught. This is the minimum potential, minimum energy configuration. So this is the stable most position, and this is called so this is the position at which the separation, the potential is minimum. We call it bond length. So in a molecule, the bond length is basically the separation at which the energy configuration is lowest among all possible values. So we can only take the diatomic molecule because it's a linear combination. But if you take the maybe a triatomic molecule or maybe some more complex shape, then it's a difficult. We need to think of gradient, you know. So what we get is called the, of course, minima, but it's different. Understood? So now we can do a modeling. There's something called modeling. So you can think that two H atoms are like two masses attached to a spring. And if you try to pull it back, if you try to increase the separation, it will attract, because this is equilibrium configuration. And if you try to compress, it will push you back. That's the idea. So the spring force that we can create is equivalently, or the K effective we can say is K times R minus R naught. Because R minus R naught is a deformation, because R naught is equilibrium position. So when you go beyond this value, if R is more than R naught, okay, let's put a plus. So if R is more than R naught, it is attractive because the net value is negative. If R is less than R naught, then this entire term becomes positive, which means repulsion. So if R is more than R naught, F is negative, which means,
So which one is the main position? Naturally,
pardon,
R or R?
R naught is the value, R is the general value, any random value you can choose.
Okay.
So which means attraction is dominant force. Okay. So every question of molecular interaction is basically modeled into the spring block system and then it is studied. So the molecular vibrations are studied as a superposition of SHM. So that you will learn maybe if you do some masters or PhD. So now what you need to be expert at is reading the graph. Like if you know how to read a graph, you're good. Now, if the slope of the potential and x graph is constant, if it is a straight line, what does it mean? The re-string force is going to be positive or negative, constant or variable? Okay, look at this. So let's say u is equals to
Variable.
minus kx or maybe alpha x. When x is between minus a to 0 and it is beta x square when x is from 0 to a. So now the graph is here. You are actually located somewhere here. This is you. This is your position at any random value x. So you are on the negative x-axis. Let's differentiate. What is force? If you differentiate, what you get? Alpha, and I will get so we have two different mathematical relation for different reason of motion. And what you can realize that in the first left of the origin, that is on the negative x-axis, the force is constant because alpha beta are constant. So the force is constant, so we can say there is a constant axis, and force is positive, which means the directional force is acting towards right. Yeah, that's interesting. So you will tend to, if you release from minus a, you will go towards the origin. But the moment you cross the origin, something interesting will happen. If x is positive, this will give you the force towards left. Because x is positive, beta is positive, 2 is positive, minus will make it negative, which means force acting left. And that is why your motion on the right side is, I mean, what you can say is decelerated. So you deaccelerate actually. On the left hand side, it's accelerating because you're trying to go towards the origin. And the right hand side, it's deaccelerating. So we are releasing from minus a, and so the equation is beta x square. So now the question is how much time it will take to go from this point A. So we have to find the so going from A to origin is easy. We can write S equals to half AT square. Do you realize this formula? It's a simple kinematical equation. You start from rest, and the displacement is A. S equals to half AT square. Acceleration is force upon mass, which is alpha by m, and this is the answer. And now finding the time from O to B is interesting. Now this is the part which I haven't taught, so I can leave it. But the way you can think is, this is a very famous equation of SHA. So you can leave this part. We'll do in, or you can revisit after learning SHA. Okay. So now this is the upper level of question that you can expect in JE. Basically, this is JE problem, but it is one of the finest problem you can come across. And this question was actually taken from the GRE problem, the SAT GRE in for admission to the US university. From there, they have taken this question. It was asked 20 years back in the GRE entrance for the US university. Anyway, so you need to just understand the or read the graph. So let's do this graph. The graph is between force and x. Okay. Do this.
X1 is unstable equilibrium, X3 is stable equilibrium.
Anyone?
So X1 is unstable equilibrium.
Stable means it should have the restoring force. So you have to just check that is the force supporting or opposing. Like if you try to go right, it should act left, and vice versa. So it's
So
stable.
X3 is stable equilibrium.
So we at which position you can think it's stable?
X3.
Correct. So x3 is the stable. X1 is unstable. How? Look at this. If you try to go right from x1, the force is acting. Force is positive, which means it is also acting right. So the motion and force are same. So it means it will take you away from the x1. And if you try to go left of x1, the force is also negative, which means it is also acting left, which means you will keep on moving left. So this is unstable case. Now look at the x3 position. If you try to go right, the force becomes negative, which means it is acting left. So your displacement is this, and the force acting is opposite, and vice versa. So if you go right or left, if the force is supporting, it means it's unstable. If you go right and left, and if the restraining force is trying to bring you back, it is stable. This is one way of getting it. The other way of getting is for stable equilibrium, the second derivative must be positive, right? So we know that force is defined as, so let's differentiate the force. What we get is second derivative, and the second derivative is minus df by dx, and this must be positive, which means the second derivative, the first derivative of force called the slope of fx graph should be negative. So now you can see at which position, if you draw a tangent to the graph, it's negative slope. You can see it.
X3.
And for equilibrium, the force, the idea is for equilibrium, the force must be zero. So at x3 force is zero, at x1 force is zero. So we have only 2 points of equilibrium, 1 and 3, because there only force is zero. And then out of these two, at x3 slope is negative, so it must be stable. And at x1, you can see slope is positive. So you can do it mathematically like this. And this is df by dx is nothing but the Okay.
Yes.
All right. So this is the graphical analysis of force, equilibrium, and so on. Let's do some more ones. So let's do this question first. U is given as a from like one dimension. A by R minus B by R square. Okay. So let's plot each graph separately first to understand the better idea. What is an A and B are positive numbers. So A by R, which is 1 by R. 1 by R means graph is something like this. Let's call it 1 by R. And 1 by R square it will decay even faster. So you can see that if I plot each term towards graph, the each term we can see it's like something like this. Okay. So now what happens is like the negative term, because A and B are positive, this is also R square is positive, so this entire term is negative. And this entire term is positive if R is positive. So it is for R positive. This is basically the two terms actually represent a repulsion and attraction. So the moment the repulsion will or attraction will balance somewhere, and I'm not saying this is attraction force, I'm saying the positive term represents repulsion, or you can say the contribution of positive comes from repulsion and the contribution of negative comes from attraction. So the negative and positive when come together, then there is a chance that somewhere it can balance. So that's called equilibrium position. So if I tell you that let's say u equals to ax square plus bx power 4 and a and b are positive. Now what we can say here, here every term is positive because even powers are positive if you remember. So here there is no negative term, which means the only one category of force is possible here, which is repulsive. This is the example of perfectly repulsive force, or which means in such formula we cannot think of equilibrium at all. So there is no need to even think of equilibrium. Okay. If you try to solve, you may get some imaginary answer, which means it is not possible. If I give you maybe So here the second term is positive for sure. What about the first term? Is it positive or negative?
So it depends upon x.
Correct. So it depends on x. So the right term is positive. So this term is negative only where in which case? Then x is negative.
X is negative.
So I can see in advance that somewhere on the negative x-axis there is a chance of equilibrium, right? So if you
Yes.
differentiate and if you get to you will get minus a by 2b, which is confirmation that on a negative side of x-axis we can get point of or position of equilibrium, because that's where the forces can be balanced. So now if you can develop this particular idea that how by looking at the terms we can decide whether the force is positive or negative, and because for equilibrium it is necessary that we must have some positive term and we must have some negative term. If by mathematical construction we make sure that it is entirely positive, which means only repulsions or repulsive forces are into the picture, there is no attractive force present, and therefore we can say that there is no question of equilibrium. So attraction and repulsion must be together to solve questions like this. So you must have come across question like this. I mean, those who have already studied. So if you write a equals to it's a very famous question. Find equilibrium position. That's the first question. Tell me the answer.
So that
Got the answer?
A is equal to 2b.
So do you know differentiation?
Yes, that understood.
So if you differentiate, what you get? R equals to 2B by A. So now if you remember the first derivative, what we got is so from there you also find the next derivative by differentiating once more. And we can take something common. Now the even power of R is positive. This is positive number. And I just want to check the sign, so I am not bothered with the value. And R power 6 is 2B by A. Because A and B are positive, so this is definitely negative. Now when the second derivative is negative, it means the potential is minimum, maximum. Therefore this is, therefore at R equals to 2B by A is position of unstable equilibrium. Okay. So these kind of questions are very common in competition. Okay. Is this clear, guys?
Yes.
So we are done with the potential and all various properties. So what we are left with is okay, we have done with work, we have done with the energy, and we are done with the okay, these two things. So the last thing is left is called power. You can also use the symbol W. So what is power? So the basic definition says that it is defined as the rate of doing work. But to do some work, we need some energy. So basically, it is also a way of thinking that somewhere some energy is consumed at a rate. Now the question is why rate is so important in physics and in day-to-day life. So when we design engine of let's say a motor vehicle, maybe car, bus, truck, airplane, the designing is very important to attain certain speed. So let's say the fuel is in the tank, and the fuel goes from tank to the engine. In engine, we have something called carburetor, which controls the flow of fluid. So carburetor will make sure that the fuel is coming to the engine at certain rate. So it will open the valve. It's a very fine hole actually. you look at, and the fuel tank will release the fuel and it will go from there to carburetor, and from there we can kind of tweak to make it flow more or less. And that is how we can get the highest speed. So now every engine is designed to operate at certain frequency.
Hello, sir.
Yes. What happened? So power will decide that at what rate I can burn the fuel. So that's called the power of the engine. So engine can burn the fuel at a certain rate, so it can produce energy per second. Now, no physical activity of the motor vehicle should consume energy more than the power which we are generating. Because once we fix the power, the energy rate is fixed, which will also fix the all external activity. So the power, if you learn, of course, we learn rotational motion. The power we write as product of torque into omega. So now the omega is the rotation of wheel, and torque is the torque which the gear system produces, called differential. So what happens is that if you want to climb on a steep slope, so let's say we have a road in a mountain area and the road is very steep, so I cannot rotate the engine at a high frequency. So omega must be very small. Why? Because to climb the motor vehicle on the steepest part, we need greater torque. Now, if you look at the engine power, the ability of engine to produce or burn the fuel is fixed. So this power is fixed. So we cannot burn all fuel at once. We can burn only fuel at a certain rate. So this is a constant quantity, and then we derive other two things. So to climb on the steepest part, the engine cannot produce power more than this, because that's the car will come with fixed power called BHP, British horsepower. So the BHP rating or specification will tell you at what rate I can burn the fuel on a best case scenario. And then if you keep the omega high, the torque will decrease automatically. So omega high refers to the high gear, and the product is constant. So always high gear refers to low torque, because here the left is constant. So the two must be managed between these two. So on the steepest part, what we do is we make the gear 1. We go to gear 1. Why? This will produce the lowest RPM. I mean, omega is least and torque is most. The tau becomes maximum. So when you're driving on the low gear, the torque is maximum, which we use for climbing the slope and on a steepest part. But if you're on a flat road, we are not trying to overcome some gravitational force. So on a flat road, what we need is just inertia to continue. So the highest gear will make the omega maximum and torque is minimum, but the product is, so your car is producing power at certain rate because the product is constant. So by minimizing the torque, I can maximize the omega because I have the choice of manipulating these two, and that is how we achieve the high speed. So we go on a gear 5 or gear 6, depends on the vehicle, gear 4, which means on a flat road you should drive at high gear if it is, of course, no traffic, and on a steep part you must put your car in the lower gear because you want to increase the torque, because you need torque to rotate the vehicle against the gravitation. Now this is some basic of driving. Okay. So power will determine the functionality of other variables. So every vehicle comes with fixed power. This is a fixed quantity. and these to be manipulated. So now this is the general knowledge about power in real life. Okay. So I can just mention this as a formula. But power we can also write as F into V. If you remember, F dot V. So again, power is generally constant. So force and velocity will be same. So let's create a vehicle first. Now this we can derive the formula quickly. So power is a rate of doing work, and work is defined as F dot ds. It is F dot V. This is called instantaneous power. It's not power of in general value. So when you take the dot product of force and velocity, what you get is called instantaneous power, and this is basically F tangential into V. That's it. If this is the velocity, if this is the force, so F tangential is how much? The force which will support the motion is F cos theta. So only the tangential force we take for power, not the centripetal force. So mathematically, we may need to define the average power. The average power is not defined this way. It's defined as total work. So we can write as, or sometimes we can also define as so work we can define in variety of ways. So total work can also be defined as change in kinetic energy. You can write like this. There are variety of ways in which you can define. So when you try to boil water in a kitchen, the LPG cylinder is burning the fuel at a rate which you control by the turning the knob left or right. And the turning the knob will only decide at what rate the fuel or the gas is coming from the cylinder to the burner. So there you produce the heat kind of. So you boil the water because the energy is coming at a rate, and that energy is getting absorbed by the water. But it is of course not the 100% efficiency. So it's not like all water is all the energy which is given by the burner is getting absorbed in the utensil. Many a part will get lost in surrounding. The kitchen gets also warmer after usage. So we define something called efficiency, which is very important. We have a symbol for efficiency, eta. It's called eta, Greek symbol. And eta is defined as output power so the actual power which we get and the power which we supply will have a ratio, will have differences. So this ratio will be less than one. You can also define percentage efficiency. Just look at it. So whenever the efficiency question will come, just write the definition and from there you can. So we know what we need here. This is what we need. And if the efficiency of conversion is known in advance, we know how much input we must supply to achieve this target. So let's say you need 100 joule, but efficiency is only 80%. So if I supply 100 joule per second, it will not work. The efficiency is 80 means I will only get 80. But what I need is 100. So what I will do is, so efficiency is 0.8. The output is known to us 100, and the input we're looking for. X will be 100 upon 0.8, which is whatever. So if you give me, or if you supply 125 joule per second, so with this efficiency, I can still get 100, which is what I'm looking for. So this kind of calculation should be handy. You should know how to do this basic calculation. That's efficiency.
So can you show the previous page? Done.
So now let's see how the real life scenario happens in case of moon. Okay, so this is the car, and the car is going towards right. So now things which you don't know, understand is this. If the car is accelerating towards right, let's say at a instant velocity is v, and the car acceleration is a. So who will accelerate the car? The answer is friction. So it is a friction force which acts at the bottom of the car, and I'm drawing the net friction. And this is the friction called static friction, which helps in accelerating forward. But because of the air resistance, a drag force is developed. And you can see that drag force will try to oppose. So now from Newton's laws of motion, what you can see? Fs minus air resistance equals to mass of the car now. So now we need to understand the energy part. Now, is the static friction doing positive work or negative work? What is the rate of doing work with by static friction? At what rate it is doing the work, positive or negative?
Positive.
It is zero. Static friction never does any work.
Zero.
Now, this is what we have discussed a lot, but I knew that this is difficult. So, in a vehicle with tires, or when you walk, static friction will support your motion. It does not mean it will accelerate you in a way by giving energy. No, it only supports. So, no energy. There is no energy relation. So, static friction never gives us energy in this case. What about the drag force? The drag is acting opposite, and you can see that the power of the drag force is minus drag into V. It is taking away the energy. So it is kind of sucking the energy. Okay. So power of the friction is 0. Power of the drag is minus F. So if the car is giving off this much energy per second, it must be deriving the energy from somewhere. And that's come the burning of the fuel in the car. So that's from the power of the engine. So now the power of the engine is kind of well known in advance. So all the energy requirement must be fulfilled because energy is taken away by the car, so it must be provided by someone, and someone is nothing but the engine. Now engine does not apply force; it only gives the energy. So power of engine plus power of static friction plus power of the air drag. So this power must be equal to the rate of change of kinetic energy because power is the rate of change of rate of doing work, and work is, we know the work is from dw is dt. So this is the fundamental equation of power. So what you need to do is you have to add all force separately. So power of force you have to add separately, then add the power of the engine. Yeah. So after adding these two, we have to add the power of engine because that is the source of energy. So now you can answer any question. If the engine stops, this becomes zero. This is zero already. So drag will decelerate actually, and so the car will eventually come to rest. If we assume hypothetically there is no air resistance, then the car will keep on moving forever without any power, and that is because of the inertia. And you can answer any question from this expression. So you can just remove or add if you have more forces, and then keep on doing. This is how we progress. The power of is decay. Now this is interesting for you. What is decay variety? So this is what you need to remember. Now comes the interesting part. The Fs is always equal to the sum of these two. eventually this will turn out to be, this is the only formula. So if you simply multiply the static friction force with velocity of that instant, you will get the power of the relation, and that this will define the kind of the maximum speed. Like we know that what we can achieve. The power of engine is constant, and a wheel is round shape, but in practice it is made of rubber. So near the bottom it gets deflated, and there is a flat patch actually. And because of that flat patch, the friction is very complex in behavior. So this is the ideal situation when we have the round shape of object. The reality is quite different. So we actually experience greater friction. So if you put a lot of, I mean, if the air pressure in the tire is very high, so the patch will become smaller in size because the high pressure it will be try to be remain round actually. So that will decrease the frictional force, which is in a way good for driving on a straight road, but at the same time it will give you less frictional force also. That's why the air pressure which is recommended by the different tire manufacturer is different. So they recommend some pressure because they want to keep the optimum value of friction force also, because that you need for turning. So near the turn, if you have more friction, it's good to turn. Okay. You can turn with ease. Okay. So the variety of things, of course, we have to ignore those things as well. So now technically we complete this chapter called work energy power, but you can okay, take some questions. So if car is, so if you drive a car with constant velocity, in that case the kinetic energy is constant of the car, so dk by dt becomes 0. So P engine plus P friction plus P drag will become automatically 0. This is anyway 0, so P engine plus 0 plus P drag, which is, so again you get the same answer. But if you use the laws of motion, you can see Fs minus Fr equals to 0 because there is no acceleration. Again, Fs is Fr, and therefore the formula will always turn out to be same. So no matter whether you accelerate or you deaccelerate, the power remains the same.
Sir, I want to move.
Pardon?
Sir, I want to move.
Now every electrical device which you purchase, let's say you purchase a bulb or a fan or everything, every appliances for, so every appliance comes with a power rating. So they mention the power at what rate it will consume the energy. So of course, those things will learn in the chapter of current and electricity, but it's the same simple. So power basically means the ability to consume energy. That's at what rate you can do something. Okay, and if the output depends on the input, so you cannot do more than input. You can always do less than input. You cannot do more than that. So I cannot drive my car which demands more power than the power of the engine. So that's ridiculous. You cannot do that. So even if you press the accelerator full, what the accelerator does is basically it opens the valve of carburetor and injects more fuel actually. So even if you press maximum, the fuel injected will have the limit, lower upper limit, and that will determine the maximum RPM you can produce. The RPM is produced inside the engine, and we have to convert that RPM into the external power to the crankshaft. The piston creates RPM, and we convert that energy. We transfer basically energy from engine to the wheels, and the transfer takes place using the chain system. With the chain attached to the wheel in case of bike. Now that chain will decide the torque on the wheel. So definitely high RPM will give you lesser torque. So your vehicle will not move very fast. So you need to put into the low gear to create the torque. Now wheel is set into motion. Omega is already achieved. So we increase the gear to decrease the torque, increase the RPM, and then so on. This is how you match the speed with gear. And in case of car, we have differentials. You can study about differential if you're interested in the like automobile sector or the mechanical branch. The differential is basically a gear system in which we allow the movement of all wheels independently of each other. It's called differential. So bike is something simple device, but car is complex device. In car we have four wheels. Okay. So when a car will turn, the issue is if you know the circular motion, when car will turn, then this will have V1, this will have V2. So how to achieve different velocity for different tires? So that means this axle is not direct. So we have a cut here, and you will see there is a round box at the rear view, and this will have a gear system. So both gear can turn at different omega and can achieve the turning. So while the car will turn, the two wheels must move with different omega, different velocity to achieve the same omega. Okay, so this is called differential. And we have a transmission axis, transmission method. So what engine produces the energy that we need to transfer to the wheels. So we need some efficient transmission method actually. And there are variety of things that we can discuss. But we're not going to this. Okay. So let's do some problem before we wrap up this topic. So let's say the power of engine is constant. That this is P naught. And you got the question. So the power is fixed. So What is the time dependence of velocity? So I want to find the velocity as a function of time t and displacement as a function of time t. Let m be the mass of particle. Okay. So to begin with, you can start with like this. You can write f as m into the f represents the net force. So we can say a into v equals to, and we can write a equals to d by dt. So v dv we can write as, and you start from rest actually. Similarly, you can find the s relation. Okay, you can do like this, or you can do it this way also. Then you can go from here. You can integrate with the answer. So this is the question. So you make a come across question like this.
So what did you do after that? B cube by 3 is equal to P naught S by M.
Pardon?
So what did you do after that step now?
Where can you tell me? Which column? First, second, third.
Third.
1, 2, 3, 4, 5, 6, 7.
So six steps. Six.
Oh, okay. Okay. You can write like this.
Okay.
Understood?
Yes.
So this was a JEE mains question. So what they asked was simple, that what is the relationship between the V and S? So we got the answer in that. The JEE mains was a proportional. This was the answer actually of JEE mains. Okay. So So as an operator of any appliance or device, you must understand the power concept. So we are done with the work in power chapter. Now we have to start something, the last topic, which is the remains of circular motion for vertical. I think this is done, right? So you
Yes.
guys have solved the numerical. So what is circular motion? We have done this before. What is circular motion?
So when a particle moves,
Okay. So it's a locus of point which moves in such a way that it's the distance from a fixed point remains constant, right?
yes.
That's the basic idea. So for circular motion, it is mandatory that the moving object must have fixed distance. So how we can make sure? So how are you going to make sure that this will happen? So we have a pendulum in which we have a string of length and bob is hanging. Okay. So first of all, we'll try to understand the concept of pendulum. So we have pendulum, we have the this is called there's something which you're not aware of as of now. It's called the length of pendulum. I may take this as small r. The idea is the length of pendulum is a technical definition. It's not a geometrical property only. The length of pendulum, and this is a very crucial concept for the chapter of SM and other chapters. Is the length of string. This is called length of string. This is called length of problem. That's the definition actually. If center of mass will change, then L will change. So length of the string you may keep constant, but as you change the center mass, L will change. So now this idea we need later on in the chapter of SHM. But right now we can just keep in mind this is the definitions. Okay. Let's put into words. And why this is so important to you to realize just now. Imagine this is some random arbitrary shaped body and this is the point of suspension. So you suspend somewhere here. And let's say this is some random location which is for center mass. This is the center mass of body. Then you can replace the body by this L. This is called L actually. So every question of a system we can or a circular motion we can solve for a particle or for body. So right now what we are going to deal with is called particle. And that's why it is not important whether you think L as the position of bob or length of string or whatever. Because what you're going to deal with in this chapter is only particle. That's why this idea, even if you don't know, will not make any difference to your life. But this idea is very important if you want to solve question of vertical circular motion from any other chapter. So let's say if I give you a body instead of particle, I may give you a rod. Then the idea we have to change from the L must be changed. Like we cannot take L the way we took in case of Bob. So we have to keep on changing the L from definition. So if I take a maybe something uh, like what? Maybe a semicircular disk. And if I suspend from here, then we know that something center mass is somewhere here. We compare. So now L becomes this one. This is the L. So in other complex situation, L will change, but the definition remains the same. So you have to think that what is L? So L is the distance between the point of suspension to the center of mass of the oscillating body. This is equally true for the bob also, for the simple pendulum also. So in our case, L is basically L plus R. But if I take if the size of the bob is very small compared to the length of the string attached, so the length of problem is as good as the length of string. So for you, the L is length of string, which is not a general way of thinking. That's a wrong way of thinking. If you think this way, you may make many conceptual mistake while solving the numericals. So this idea is very important. That what is L? L is a technical definition. Okay. So imagine you take a big balloon and you fill with water and you prick a hole at the bottom. So water will leak out slowly. And then you set into oscillation. Now here the center mass is here at the very beginning because the ball is completely filled, but after some time the level of water is not complete, right? So water is only up to hit this side. This is a plastic ball, it will not shrink. So now water is only this much. Now center mass will go below actually, somewhere here. So the length of pendulum will grow actually. So if you see the situation, the length of pendulum will first grow. But once it is empty, the center mass will go back to same point. Yeah. So this is the example of the oscillation in which the length of pendulum is varying continuously. And therefore, if I choose the variation to be small enough, like the variation is happening slowly, the time period of oscillation will first grow in value. That will continue. As L will become more, the time period becomes more actually. We have a formula something like 2 pi in the root. Might have seen before. As L will grow, this will grow. Now this L is not length of string. This L is actually the definition which I just gave you. So someone not knowing this definition will make a mistake because they don't understand what is L actually. L is something very bigger than what you think or what you believe. So I hope this concept of L is clear to all of you. Now the SHM of the vertical motion of a rigid body we will take care separately in a chapter of rotational dynamics. But right now we have to take care of the string and bob part. And the biggest challenge to achieve this task is that the separation between the point of suspension to the bob that should not change, right? Because as we're looking for is called vertical circumference, so we must keep the direction constant, the separation constant. So now, if I throw it tangentially with some initial velocity, the separation between the bob and the center suspension, the O and the bob, this must remain same, right? Here also. So how we can make sure that this will happen? What is the way to make sure this will happen? How we can make sure that the separation between the bob and the suspension remains always L? So what is the mathematical condition which will assure us that okay, L is safe, L will not change. The separation of the center of bob to the suspension is not changed. So what is the mathematical way of doing this? Tell me. Simple answer is by keeping the string taut. Now, this is a mathematical constraint that we can impose to make sure that it moves in circular path. Now, what will happen if tension becomes zero?
The string will snap.
So, what is the meaning of tension is zero? The only force acting on the body will be
No, M,
which force will act if
MG,
tension is zero?
MG, MG.
So, the only force acting will be gravity, right? And if the only force acting is gravity, then what will be the path of the bomb?
Down.
Path, the shape of path,
Parabola.
parabola. It's not circle. Now, this is the most important part which you need to remember and understand that the motion under gravity cannot be circle. It is always a parabola, which may be as good as circle, but not a circle. So, the moment you make the tension zero, the body comes under gravity, and under gravity, we know the path is parabola. So, that is what we have to prevent. So, at no time or no point of motion, the only force should be gravity. So we have to sorry. We have to make sure that the force is so we have to make sure that at no point of journey the tension is
0.
zero. So now we must choose a point where the chance of getting it zero is highest. And we can see the point is the topmost point.
So what?
So at the topmost point, the chance that tension will be zero is very high. Why? So look at the FBD of this point. So the tension is like this. So from the concept of circular motion, what we can write?
And U square by R is equal to P plus NJ.
From dynamics of the net force towards center equals to mv square by r. So it means at this point we must have some velocity which I need to check how much. Let's call it bc. And both the force are acting towards center. This must be equals to the r will be replaced by l by definition. Which means we only look at the motion of center mass. We don't see the motion of body. The r is the distance between the point of suspension and the center mass of the body, and that is always true. So here the r will be l in this body. So this gives us everything. This is a mathematical constant which we need to play with. That's it. So for VCM, if I can make sure that TC is positive, then other points are definitely going to be positive. And TC is how much? Which makes sure that the VC square is more than GL. This is, so if I somehow I can manage the velocity at the point C more than value GL, root GL, I'll confirm that the motion will remain indeed circular and nothing will, it will never slack in anywhere. Now this is the answer actually. Now what generally we answer is the minimum possible value that can make sure that it's a circular motion. So for VC minimum, it is roughly equals, not exactly. Now while solving numerical, we take it exactly equal. It does not mean it is exactly equal. It is actually slightly more than this value, which is negligible. How more is 0.00000. So the minimum we take as root GL, which will make sure this will happen. If it is more than root GL, it's good. So now we know the mathematical condition for circular motion, and the condition is at the topmost point, the velocity of particle should be this much. Now knowing this in this as a constant relation of VCM, we can go back to the values at bottom and the rightmost and so on. So for VA minimum, what we can do? So here energy is not lost, so we can just conserve the energy and we can get the answer. So you can conserve energy from A and C. So choose reference as you wish, and then add the answer you get. You can also do the work yourself. Up to you what you feel comfortable. So this is the only basis of thinking. So let's take and I have taught you how to do this. Because from reference it is 12 above. So if you solve by substituting modalities, and similarly if you solve you get the answer 3GL for TG. And then what you can do is you can do for the other points. Okay. So what I'll do is, because I'm deprived of time and I'm not also well actually. So I'll share the notes of VCM. You can just read through it. I have solved every question which is possible in this chapter. Theory is only this much. This is the only theory, rest is only numericals. And because you have already solved, so this culminates the entire vertical circulation. And so the work in power chapter we are done. So after the break, because I'm going for a break, we'll start a new chapter called center of mass, which is very easy chapter compared to all these chapters. But you need to be very good with energy consideration and circular motion and everything else, because that will be we are going to again use in the chapter of rotational dynamics. So rotational dynamics is some sort of application of entire mechanics, whichever you have learned so far. So now difficulty level will grow in terms of concepts used, but eventually it remains the basic one. So we have to add a variety of components to solve one question. So you need to add laws of motion, kinematics, energy, circular motion, and everything else which you have learned so far to solve one question of center mass. In that way, it's very difficult. So we'll learn step by step, not to worry, and hopefully we'll master the chapter of center mass and rotation also. And once you're done with these two chapters, then trust me, the class 12th is just time pass. It's like there's nothing as a soul is nothing. It's very hollow in nature. So all good questions of class 12th are based on these chapters. So someone good with the mechanics can do any question of class 12 with ease. So this is where I'm ending this chapter, and I'll share the notes. You can just read through it. You will get it. Okay, guys. Bye.
Bye, sir. Thank you, sir.